With every detailed look we take into the universe, we encounter objects of immense diversity. Each of these celestial bodies possesses distinct yet highly crucial characteristics. In particular, exoplanet discoveries, which have seen accelerated research in recent years, leave us profoundly astonished after each new find. Among these exoplanets, one that has personally amazed me is a world that could be entirely covered in water, or rather, liquid. Perhaps you have heard of this planet before. It is TOY 1452b. Today, we will take a detailed look at the specifics of this planet, its discovery process, and the statements made by scientists regarding it. But before we dive into our video, if you enjoy this kind of content, don't forget to like my video, subscribe to my channel to support me, and finally, leave a comment to share your thoughts. Now, if you are ready, we can move on to our video. For anyone who studies and feels a sense of wonder toward the universe, there are essentially a few fundamental questions. One of these is whether life is a phenomenon exclusive to Earth. When we seek an answer to this question, perhaps the most critical criterion we look for, as you can all guess, is liquid water. Water is the cornerstone of biochemical processes as we know them. This is due to its properties, such as its solvent capabilities, its role in thermal equilibrium, and the flexibility it provides to molecular interactions. Thanks to these features, water provides an indispensable medium for life to emerge and be sustained. For this reason, in modern astrophysics and astrobiology studies, the potential of planets orbiting stars to harbor water is examined first, rather than their basic physical characteristics. In this context, the planet TOI 1452b, discovered in recent years and causing a great stir in both the public and scientific communities, stands out as a strong representative of a new class of planets called ocean worlds that challenge classical definitions of terrestrial planets. The planet TOI 1452b is located approximately 100 light-years away from us and is an exoplanet orbiting a red dwarf star. Its mass corresponds to roughly 5 times that of our Earth, while its radius is about 1.6 to 1.7 times larger. These values place it neither in the category of small rocky planets completely resembling our own, nor in the class of gas-rich planets like Neptune. Such bodies are called super-Earths, and light shed by observations made particularly over the last 20 years has revealed that they are quite common in the galaxy. However, the most fundamental feature that distinguishes this planet from other defined super-Earths is that its average density turned out to be much lower than expected. Scientists, in their statements, expressed that they were highly surprised by the situation and were looking for answers to explain it. The density of TOI 1452b is too low for a completely rocky planet, yet not low enough to require it to be a gas giant. When you know a planet's mass and radius, you can calculate its average density, and through this calculation, you gain strong clues about the planet's internal structure. This allows you to make accurate predictions about the planet. Anyway, the fact that the planet's density is low for a terrestrial world, but high for a gaseous one, gave rise to the hypothesis that a significant portion of it consists of water. Modeling indicates that approximately 20% to 30% of the planet's total mass could be water. While this ratio might seem low to you at first, this amount of water actually corresponds to hundreds of times the total amount of water on Earth. At this point, it is especially emphasized that the concept of water is not limited to its familiar meaning on Earth. On high-mass exoplanets like TOI 1452b, as depth increases beneath the liquid water that may exist on the surface, pressure rises dramatically. Under these pressure conditions, water forms crystalline structures entirely different from the ice forms observed on Earth. These phases, referred to as high-pressure ice, cause the density of the water to be higher than its liquid state despite transitioning into a solid form. This situation leads to unusual stratification within the planet's internal structure. While a vast and deep liquid ocean exists on the surface, high-pressure ice layers hundreds of kilometers thick can lie beneath this ocean. Below this ice layer, there is a rocky core composed of silicates and metals. Consequently, TOI 1452b may not be a world covered in water in the classical sense, but actually possess a much more complex and stratified structure. Furthermore, another remarkable feature of this already intriguing planet is its distance from its star and its orbital period. Despite having a short orbital period of about 11 days, it is located within the habitable zone thanks to the low temperature of the star it orbits. This situation alone tells us that the planet holds special characteristics for us. This is because both having a short orbital period of 11 days and being located in a habitable zone is not a scenario we frequently encounter in the universe discovered so far. Because the red dwarf stars that the planet orbits emit much lower energy compared to the Sun, the habitable zones are located very close to their host stars. This allows TOI 1452b's surface temperature to theoretically remain within ranges that can support liquid water despite its proximity to its star. However, an important complexity emerges emerges here that should not be forgotten. Red dwarf stars generally produce intense stellar flares and high-energy radiation. This radiation can erode the planet's atmosphere over time and negatively impact potential conditions for life on the surface. If a planet orbiting this type of star does not possess a strong and thick atmosphere, it will be heavily affected by the star. In other words, even if the planet is located in the habitable zone, there are certain conditions it must meet. That is why it needs to have a very thick and strong atmosphere to prevent it from turning into a planet like Mars. Therefore, a planet's presence in the habitable zone does not mean it is suitable on its own. Many factors such as atmospheric stability, the presence of a magnetic field, and stellar activity must be evaluated together. Now, let's come to the discovery process of this magnificent planet. First of all, I need to state that in recent years, we can make highly detailed and precisely accurate observations thanks to both the observation instruments we have sent into space and the advanced telescopes we have built on our Earth. Moreover, thanks to engineers and astronomers, our technology in this field is developing every year, and we can even say this: space agencies now prefer sending robotic vehicles into space and making detailed observations from Earth rather than traveling to space themselves. This is because it is both less risky and much more advantageous in terms of cost in the long run. The discovery of TOI-1452b was achieved using the transit method, one of the most precise observation techniques in modern astronomy. In this method, when a planet passes in front of its star, a decrease, even if in very minute amounts, occurs in the light coming from the star. If this decrease repeats periodically, it points to the existence of a planet. NASA's TESS telescope constantly scans wide areas of the sky to detect such changes in brightness. TOI-1452b was initially identified through this method, and its existence was later definitively proven with additional observations. Furthermore, the transit method allows for the determination of not only the planet's existence, but also its radius. However, additional methods are required to determine its mass. At this point, the radial velocity method comes into play. The planet lightly wobbles its star via gravitational effect, causing a Doppler shift in the star's light spectrum. By measuring this shift, the planet's mass can be calculated. These measurements carried out for TOI-1452b revealed to us that the planet falls into the super-Earth category and that its low density can be explained by the presence of water. So how does the formation of this type of planet take place? For instance, do you think it has a formation and development process closer to terrestrial planets or to gaseous planets? First of all, to understand the formation process of such a planet, it is necessary to look at planet formation theories. While stars are formed by the collapse of giant molecular gas clouds, a protoplanetary disk rotating around them occurs during this process. Since I have already explained this event to you many times in my previous videos, I will not explain it now. However, within this classical process, the temperature inside the disk varies depending on the distance from the star, and water vapor beyond a certain distance condenses and transitions into ice form. This boundary is referred to as the snow line or frost line in literature, and planets forming beyond this frost line contain abundant water and volatile matter. The fact that TOI-1452b possesses such a high water ratio at its current location indicates that the planet most likely formed beyond the frost line initially and then migrated toward its star for some reason. The phenomenon we call planetary migration is a very common process, especially within young stellar systems, and the orbits of planets can change over time due to gas interactions within the disk. Now that we understand the formation process of the planet as well, we come to perhaps the most important question for this planet. Could life be possible on a planet like TOI-1452b? Honestly, it is quite difficult to say yes or no to this question in a definitive tone, because our current technology is not sufficient for us to give a definitive answer to this question, but of course, scientists have a series of theories for it. For example, if a vast liquid ocean exists on the surface of the planet, this ocean could provide a suitable environment for life. However, the ice layer formed under high pressure could cut off the contact between the ocean and the rocky core. For instance, on our Earth, hydrothermal vents located in our oceans are of critical importance for life. However, if such vents do not exist on the planet and there is no contact with the core, the probability of life decreases considerably. Along with this, it should be kept in mind that completely different biochemical processes could also be possible. High pressure, different temperature gradients, and chemical compositions can theoretically allow for life forms entirely different from those on Earth. However, because we cannot examine the planet in detail right now, we cannot know whether such a situation has occurred or not. Additionally, it is expected that this planet's atmosphere will be examined in detail in the future, yielding clearer information about its potential for life. Advanced observation tools like the James Webb Space Telescope can analyze the starlight passing through the planet's atmosphere to determine its chemical composition, and the presence of gases such as water vapor, carbon dioxide, and methane also gives very crucial clues about the physical conditions of the planet. Especially the coexistence of the methane and oxygen duo could signal to us that biological processes have begun or have already begun and shown development. However, such analyses are extremely sensitive and their interpretation requires complex models. Furthermore, scientists make a series of predictions regarding the internal structure of the planet as well. For example, while the deepest point of the oceans on our Earth is limited to about 11 kilometers, according to predictions made, the depth on this planet could reach hundreds of kilometers. Such a deep mass of water creates incredibly high pressures in the lower layers, and the behavior of water at this pressure goes beyond classical liquid-gas-solid phase diagrams. Exotic phases known as high-pressure ice emerge, which are the ices I mentioned at the very beginning that possess a different density and crystal structure than the ice on Earth. Moreover, this situation causes the water to not rise toward the surface despite freezing in the lower layers. In other words, the scenario on Earth where ice floats on water is not valid on this planet. Instead, high-pressure ice forms a stable layer beneath the liquid ocean. Although the things we know about this planet are limited to these for now, it is certain that we will learn much more things in the coming years as our technology and devices develop. Who knows? Perhaps right now in the depths of the ocean on that planet, magnificent creatures exist and are waiting for us to discover them. As someone interested in space and astronomy, I hope that I can witness these discoveries and see that planet live. Thank you for watching me. Unfortunately, that's all from me for today. I hope you liked my video. If you liked the video, don't forget to hit the like button, subscribe to my channel to support me, and leave a comment to share your ideas about future videos. See you in our next video. Goodbye.